Good morning, students. Am I audible? Hello.
Yes, sir, you are audible.
Hello. Am I audible?
Yes, sir, you are audible.
Yes, sir.
Is the screen visible? Presentation?
Yes, sir.
Okay. So let me start.
Yes, sir.
How many of you joined? Only 11 people. Anyway, I don't think I should. Okay, so as I have discussed last day, today I am going to uh, discuss a very important problem regarding graph data structure, using graph data structure, and this is very useful in solving many problem in many different domain of computer science, which is called topological sort. And this topological sort is basically defined on directed acyclic graph. So as you have already seen, the definition of directed acyclic graph means a directed graph which contain no cycle. There should not be any cycle. It will be a directed graph having no cycle. Okay. Now we'll find there are many applications where we can represent the relationship between the entities which are involved in that problem using a DAG. Okay. And here the nodes, we need to order the nodes in order to solve the particular problem in a manner which is called topological sort. So let me motivate the topological sort with a very popular problem like scheduling. The scheduling is important in case of operating system job scheduling, or when we have parallel processing for assigning different tasks to different CPUs, available CPUs in a proper manner to optimize the time of completion. And also you will find at the end I will show that this topological sort may be useful in simulating a digital circuit also. Okay. So let us take a very hypothetical small problem that we have a set of statements. Okay, computational statement. As you can see, there are 4 computational statement, very naive and simple computational statement involving few variables. Now the question is, suppose these statements are not ordered in proper manner, like they are presented in a haphazard order. Now you have to fix the order of the execution of this statement in such a way that the data dependency is not conflicting. Like as you can see, the input of one statement here is dependent on the output of some other statement, maybe more than one statement also. So now the statement whose input depends on some output of some other statement, the ordering should be such that the latter one, the whose output is going to be fed into the statement concerned, should be evaluated first. Unless the output is available, you cannot execute or evaluate the statement whose input depends on that particular statement. So in this way we have to order. Or even if you think of parallel processing, suppose you have a set of n statements. Now you have more than one CPU available with you. Now, how do you assign the subgroup of these statements to different CPUs so that each CPU can perform their set of tasks sequentially without violating any dependency constant? Otherwise, suppose if you have assigned one statement to CPU 1 whose input depends on some statement which should be evaluated by CPU 2, there will be a conflict. You may not get the proper advantage of parallel processing because CPU 1 has to wait unless and until the particular statement gets executed by CPU 2. So in any case, a single CPU execution or multiple CPU execution, you have to order the set of statements in such a manner that data dependency constants are satisfied. That is the motivation. Now, how do you solve this problem? So before you solve, you can easily see, you can pre-process this thing by modeling or this set of statements, considering each statement as entity, modeling the data dependency in terms of a directed graph. Like you start with the variable which are independent variable whose values uh, will be collected from user, or maybe there will be some assignment statement, initialization statement, which will have the value of the independent variables. Like here a, b, c, d, you can see that these are independent variables. Okay, all the statements here in the left side are dependent on the values of these four variables. Okay, now you can easily see that once you know the values of a, b, c, d, now which statement you can evaluate? All the statements which involves only a, b, c or d can be evaluated in the next step. So the first statement, which is e equal to a plus b, can be evaluated next because both a and b's values are available. Similarly, this second statement also, second statement cannot be evaluated because till now the value of e is not available. Okay, so third statement depends on values of c and d, so that can be evaluated. So here is the construction. So these two statements. Now once these two statements get evaluated, next the third statement which depends on a and e, now both of them are available. So that can be evaluated in the next step. And finally, in the fourth step, the fourth statement can be evaluated. So in this way, we can construct a directed acyclic graph, which is sometimes termed as data flow graph or data dependency graph or sequencing graph, like this. The same name, same graph may be referred by different names. The idea is it just this construction of the graph actually takes care of the data dependency of these input statements. Okay.
Sir,
Yes.
after evaluating the first statement, we can evaluate the second also, no, sir? You said A, B, C, D are known. From first statement, we can calculate E also. So second also can be evaluated.
Second means which one? G.
Yes, sir.
No, see G. See, first level I have the independent variable. Now in the next level, which statement can be evaluated? Those statements whose input depends on only A, B, C or D. You can see easily that this second statement depends on E, which is not an independent variable. E has to be evaluated by evaluating this first statement. Unless this first statements get executed, value of E is not available to you. Understood?
Yes, sir.
Okay. So in the second step, you cannot evaluate simultaneously this first statement and second statement, because here first statements get executed, then so each of these operations will take some amount of time. There will be some latency. So after that latency, the result of E will be available. then only you can execute the second statement. But you see third statement whose input depends on C and D, which are independent. So third statement and first statement can be evaluated concurrently. Concurrently, obviously, here I am assuming that the hardware required for addition and hardware required for multiplication are separate. Okay. That adder and multiplier, two units within the ALU are distinct. With that assumption, I am saying that these two operations like statement 1 and statement 3 can be performed concurrently. Or if we have two dedicated CPU, then also these two can be operated concurrently in the same time step. But whatever may be the number of CPUs you have, whatever number of different instances of adder multiplier you have, you cannot evaluate this statement like this first statement and second statement concurrently because there is a data dependency. That is the whole idea. Are you getting my point?
Yes, sir.
Similarly, in the third step, you cannot evaluate the second statement as well as fourth statement because fourth statement needs the value of G, which will be evaluated after evaluation of this statement. Though F is available, but the other operand G is not available, so it has to wait. So it has to wait up to the fourth time step. So this is the whole idea of construction of this data dependency graph. Have you got that?
Yes, sir.
Okay. So it will always be this type of problem. If we try to model it as a graph, directed graph, it will be always a directed acyclic graph because it cannot hold a cycle. If there is a cycle, that means this entire set of statements cannot be executed. I mean, you cannot have a cycle, then the whole set is invalid. No one can evaluate properly. So it will not have a cycle. So you think of a large number of statements having several data dependencies among them, you can represent that using a directed acyclic graph like that. Now, in order to find the order means you have to consider that you have to assign different statements, evaluation of different statements at different time step. Like this may be called 0th time step or 0th level, that you can just get the values of independent variable A, B, C and D in the 0th time step. Now in the first time step, you can evaluate these two statements in any order. See, ordering between plus and the star operation, that means ordering between this first statement and the third statement doesn't matter. If you have dedicated hardware for addition and multiplication, or you have dedicated CPUs, these two operations can be evaluated concurrently at the same time step. That means time step 1 or level 1. Similarly, this second statement can only be evaluated at time step 2 or level 2, and finally the fourth statement can be evaluated at time step 4 or level 4. This is the idea. So here this is a very small example, so you can easily just constructing the graph, you can find the order of these four statements. That means statement 1, statement 3, then statement 2 and then statement 4. This is a valid order of evaluation of these four statements, and you can easily see this ordering between this group of statement 1 and 3 is not important. Like you can have another valid order, that 3, 1, 2 and 4. Do you understand? The ordering between these two statements in the same level can be arbitrary. Okay. So this is a possible scheduling, that time step T1, this O1, O2, O3, O4. or time step T0 you can say, no problem. It can start from T1 to T4 or T0 to T3. That doesn't matter, you know. Okay. Similarly, in time steps T2, this may be these two operations. Time steps T3, this operation, time step T4. And see, this is not unique because this, I mean, this scheduling is unique, but ordering you can say O1, O2, O3, O4, O5, O6, O7, O8. Or another possible ordering may be this O2, O1, O4, O3, O6, O5. So within these labels, the operations can be ordered in any arbitrary order because they are not dependent. There is no dependency between these two operations or these four operations. That is the thing. But obviously, your target would be to find out any one. If you can find out any one such possible scheduling, then your job is done. Now, how do you find this? So this is another possible scheduling. Okay, because see, this O6, you can defer the execution of O6 to the next level also. No problem, because executing this in time step T1 or T2 doesn't matter. Because ultimately, the execution of the last statement depends on both of them. So this is also a valid ordering. Okay. Now, how do you find? So when you have a large set of statements, how do you find such an ordering? What will be a formal mechanism? Can you suggest? So pictorially, what will your solution expect? That these arrows, whatever way these arrows are pointing in the directed acyclic graph thus constructed, should be in such a manner. See these arrows. Okay, it should point top to bottom. There should not be any back arrows. Okay, so this levelization should be done in such a manner that data dependency constraint is satisfied. Okay, and this is basically ordering all vertices of data flow graph or data dependency graph V1, V2 up to Vn such that for every edge Vi, Vk in E, I less than k. That means your edge, whatever edge, in such a way you have ordered any edge which starts from ith node to kth node, since k appeared after I, okay, in the order. Similarly, the edge should also point from I to k, not k from I. Okay, because Vi is the input which must be evaluated first, then Vk can be evaluated. And that is the whole idea of topological sort. So for a directed acyclic graph, a topological sort is an ordering of all of G's vertices such that for every edge Vi, Vk, okay, in the edge set, I should appear before k in the ordering such that this dependency, this arrow is like coming from left to right or top to bottom in the graph. There is no back way you have to go. This is visuality. Okay. So I am showing an example. Suppose this is the graph. This is the input graph where you can see visually there may be several edges that are coming from right side to left side. Now, if I order 3, then 4 in my ordering, that will be an invalid topological sort because the edge 4, 3, edge is actually going from 4 to 3. Now, if in my ordering 3 appears before 4, that means that will violate this dependency constraint. When there exists an edge from 4 to 3, that means whatever way I sort, 4 should appear before 3. That's the point. So I have drawn a very bad picture as a solution. You can see if your ordering is such something like this, 1 comes first, then 2, then 5, then 4, then 3, then 6, then 7, then you can easily see visually all arrows are pointing from left to right, and all data dependencies same set of edge, that I have not changed the edges I cannot change. There will be 4 to 3, see 4 to 3 is there, and it is pointing towards from left to right. That means 4 appears before 3, which is desirable. This condition is saying if there exists an edge between Vi and Vk, Vi must appear before Vk in the topological sort. Understood? Is it understood? The meaning of topological sort?
Yes, sir.
See, anybody is having any difficulty, please. Okay, so you just check for this graph that possible topological orders. As I have said, it may not be unique. There may be several topological orders, valid topological orders. But for any problem, real life problem, finding one of them will be sufficient. And you should remember that there will be a subset of the nodes which will appear in the same level, though they are appearing, it's like a sequence, but you may find that there may be some particular nodes whose order may be changed between themselves. Okay, like this 7, 3, 6, these 3 nodes, they may appear 3, 6, 7, 7, 3, 6, 7, 3, 6 in any way, because they don't have any dependencies among them, and that makes this topological order non-unique. Understood? Now, given a directed acyclic graph, how do you find, what will be your strategy to find a order, such a order? Any one of this valid topological order. Can you suggest? Can you suggest something? Anybody? Hello? Anyone can suggest some solution or approach for finding a topological order? Am I audible?
Sir, we can start from those nodes which don't have any incoming edge, like they will be done first, right? That job
Okay.
will be finished first.
Okay.
Then we can mark all adjacent with something like, then this is the next one and this is the next one.
Okay. You
Sir,
are
can
going
we
into the
use
correct.
DFS?
Huh?
Can we use DFS for solving this?
Yes, you can use DFS, but I will discuss that. DFS is a very elegant way of solving this problem, but what Vishal was saying is also correct. There is an algorithm. So, first of all, we need to check that in a directed acyclic graph, we will always be able to find at least one node which do not have any incoming edge. That means this independent variable. Okay. any directed acyclic graph, at least one node. Here see, you can find this, you can easily see this, there are two nodes 1 and 2 which do not have any incoming edges. Okay, it is always guaranteed. You can, if you look at the construction of directed acyclic graph, you will be, it will be guaranteed that there will be at least one node, at least one if not more, which have no incoming edge, and we call such a node as root. So first of all, a naive strategy would be like that. I will just perform a pre-processing on this graph to store the number of in degree of each of these nodes. Okay, and sort them first in terms of their in degree. And as I have said, I will at least find one node which have in degree 0. And that if there are more than one, I will choose any one of that in degree 0 node as the starting point of my topological sort, which I will call root. Okay. Then what I will do, I will pick up that node and make that node as the first node in my order. Then suppose this is 1. Okay. Now once I have chosen 1 in my ordering, that means all the other operations which depends on the output of 1, their data dependency is resolved with respect to 1. See, 3 is dependent on the output of 1 and 4 is also dependent on the output of 1. So now I can just remove these two edges because these data dependencies is resolved. Since I have already considered, one in my order, that means data dependencies associated with 3 and 4 with respect to 1 is resolved. Maybe they have some other data dependency that will remain. So I can silently remove these two edges and then I can update the number of in degrees of the remaining nodes, because the in degree of these two nodes will be decremented by 1. And again I will search for another node whose in degree is 0 and I will repeat this thing. I will choose the node having in degree 0 in the remaining nodes to be put into the order, take that node in my order and also remove all outgoing edges emanating from that node which I have considered and repeat the step iteratively unless and until I will be able to exhaust all the nodes. Okay. So this as I have already mentioned, this cycle cannot be there. It is guaranteed. That's why I can just follow this strategy. So I will assume that in degree is stored with each node. If it is not, I will perform a pre-processing. Then I will repeat until no nodes remain. Okay. Choose a root node with in degree 0. To start with, it is guaranteed that I will have a 1. And when I am actually decrementing the in degrees of other nodes, I will find at each step, at least I will find one node whose in degree was non-zero has become 0. Okay. So it is guaranteed. You can easily check. Because whenever I am considering one node in my ordering, I am picking up that node, I will remove all the edges that are emanating from that particular node, thereby decrementing the in degrees of some other nodes to which it was connected. Okay. So this is the formal algorithm of this strategy. I am not keeping that here. I am just illustrating it. Let me illustrate the strategy. So here, first I have this L and this is the S, means that in degree 0 node. Okay. 1 and 2. So any one I can choose. Let's say 1 I have chosen. Okay. So once I have chosen 1 in my sorted order, I have removed the edges here. And the in degree of other these two nodes which were connected with 1 will be updated. Like in degree of 3 was 2 earlier and 4 was 3. Now their in degrees will become 1 and 2 respectively. Okay, so but fortunately you see 2's in degree was 0 already. In this first step, no new node have been added in this list because both 3 and 4, although their in degree has decremented by 1, but they have not become 0. But it will always be guaranteed that there will be a node whose in degree is 0 will be present in this list. So here 2. So I will pick up now 2. So this one picking up 1 and 2 or 2 and 1 is arbitrary. Okay. But anyway, without loss of generality, let us choose that we have chosen 1 and then 2. Now once I choose 2 in my order, these two edges will also be removed. And now see, it will decrement the in degree of 4 and in degree of 5. And in the process, the in degree of 5 has become 0, so it will be included in the list S. Okay. So next I will pick up 5 and I will remove all the outgoing edges from 5, and by doing so I find that in degree of 4 has become 0, so it will be included in S, and in the next step 4 will be included in the topological sort and all the 3 outgoing edges will be removed, and eventually 3 and 7 both of them will have in degree 0 and again they will be included in S. Now picking up 3 and 7 is arbitrary. I can pick up 7 first, 3 then, or 3 first and 7 then, no problem. But here without loss of generality, let us include 3, and so this will also give rise to in degree 0 for node 6. So S will be now modified as 7 and 6, and finally I will choose 7 and 6 in any order. Okay, so this is the simple strategy for solving the topological sort problem on DAG. Okay, and as you see, I've been able to find one order. You may find this applying same strategy. You may find a different order when you actually break the tie between when you have multiple nodes at any step in S. Which one you will choose? You have the liberty to choose any one, and based on that, this particular order may get changed. No problem. Any valid sort will be useful. Okay. Is it okay?
Yes, sir.
Okay. Although this strategy is very simple, but it may not be very efficient. Okay. Because you can easily see that the performance will be roughly order of V square, where V is the number of nodes. Because first of all, in order to pre-process, in order to count the in degree of every node, you have to perform a traversal of all nodes. Okay, count the in degree and sort them. Okay, so you may find a linear search to find a root first. Okay, so that will be V, and then for every node you have to do this removal of edge and all these stuffs. Okay. Now, as Sonkita was suggesting, so this particular thing will be implemented using a stack, as you can easily see that pop a root. So scan all nodes, pushing roots onto stack, and then pop a root from, I mean, this is just an implementation of the strategy I have shown. This is quite evident. You just have a look on this. Fine.
Sir, this is BFS based.
Yes.
Is this BFS based? Or because we are using
It is
we
not
will be
exactly
traversing
DFS
in
based.
different
I mean,
nodes.
You just you assume that the integers are available as a starting point. Now you have a list of all nodes. That means the graph VE, the V is available. Along with that, you assume for each V1, V2, V3, their integers are also stored.
Yes, sir.
Okay.
So
Now,
we will store the integrity in the stack.
yes, you will just scan the perform a linear search to find out the root, one root. Then you will pick up that, and then you will put into the list of your topological sort, and you will go to the edge list to find out which edges are connected or emanated from that particular root node you have chosen in this step, and accordingly you have to again go to this list of vertices. You have to reduce the integrity there. In this way you have to go. Okay,
Okay, sir.
fine. It may not be exactly a BFS because there will be some arbitrary movement. It is a list based, and then you will be able to use it in a stack. Okay. Now, DFS, as Sankita was suggesting, will be a very elegant way of solving this topological sort problem. And the whole idea is, again, you have to classify the nodes while you will perform DFS as the heart of the solution. You have to classify each and every node with three distinct levels you have to attach. One, you can say unvisited, that means which you have not yet visited through DFS. So let's say that level is U. And then there may be a node which you have visited through DFS, but its job is not completed because you have not completed traversal of the entire subtree. I mean all descendant nodes yet. Okay. Unless and until you complete visiting all the descendant of a node, that node, even if you have visited that particular node, it will be labeled as incompletely visited. Okay. And finally, there will be another level called completely visited, when a node is not only visited through DFS, but all of its descendants have also been visited. Okay, so these three different levels you have to use, which will make your topological sort solution very elegant. Okay, now what you will do, you have to perform DFS and output the vertices in the reverse order of getting the status C. So you will just perform DFS and you will just complete the DFS. When the entire DFS will get complete, all the nodes will have the level C. Okay, now you will just keep a record that which node is getting the visited status first, then which node is getting the visited status next. In this way you will keep a record, and then you just print the order in a reverse order of getting the status C. That means you have to output the node which gets the visited status at last, which will be the first node of your topological order. Got my point?
Yes, sir.
Okay. So while performing DFS, the ith node getting the status C is assigned a sequence number. You can easily while doing this thing, you can keep track of that dynamically by assigning a number. The number will range from 1 to the number of vertices. Okay, and automatically you will be able to get the topological order. I'm illustrating that how you can number, this step while performing DFS. The ith node getting the status C is assigned a sequence number V, that means the maximum node number minus I minus 1. Then automatically all the nodes will be assigned the number which will be the topological order number there. Okay, Let me illustrate using an example. Suppose this is the directed acyclic graph which is input to us. Now you see that all the nodes initially have level u because no one is unvisited. Now as you can see, for DFS you can start from any node. You can start without loss of generality. Suppose this node you start, this A. Okay, now when you start with A status will be changed from U to I because it is just visited, but you are not sure whether all its descendants have been visited or not. So it will be given the level I. Okay. Now DFS will say that you either go to D or go to E because those two are directly adjacent with A. Suppose you have visited D next. So this edge you have, through this edge you have visited A to D, and then the status of D will be changed from U to I. Now while coming D, you have two options. Either go to F through this edge or either go to E through this edge. Now suppose you have gone to E. Okay. Now the status of E will be changed from U to I, and next from E there is only one way to go to F. Accordingly you will go to F and the status of F will be changed from U to I, and from F you have only way to go up to H, and accordingly status of F will be changed to I. H will be changed to I. Now from H you are sure there is no outgoing edge. So now you can set the status of H as C. Okay. This is, so this C is getting the first node. C is assigned the status completely visited. So you can give a number. What number? Since there are 8 edges, 8 nodes, 1, 2, 3, 4, 5, 6, 7, 8, this will be the last node. As I have said, that the first node that is getting the completely visited level will come at the last in my topological order, and so this number of nodes minus I minus 1 will give me this 8 in this particular case. So this will have a sequence number 8. And after that what I will do, I will backtrack to F, the parent of H, to check whether it has any unvisited descendant or not, where I found that there is no unvisited descendant for F. So F will also get complete status, and accordingly F will get a sequence number 7. Now from F I will visit the parent of F, which is E, where I found that all the descendant node of E is already visited. So E will also now get completely visited status, and it will have a sequence number 6. Similarly, when I move to D, parent of E, there I find that this edge was unvisited, but this node, descendant node, has already been visited. So D will also get complete status. So this particular edge will not become the part of my, it will not be the tree edge, but that doesn't matter in this particular case. I will just check whether the descendant node has already been visited. It is visited. So D will get a complete status, and accordingly D will get the sequence number 5. Similarly, when I move to the parent of D, that is A, where also I find that all the descendant of A has already been visited. So A will now get the completely visited status, and accordingly the sequence number 4. So this complete one iteration of DFS. Now still I have some unvisited node, so I have to start from once again. let me start from this B, node B, and change the level of B from U to I, incompletely visited. Then what I see, that there is only one descendant node E which is already visited. So automatically B will get a completely visited status and it will get a sequence number 3. Then I have to again start, because this is complete. I mean, there is no way I can go further. So let's start with C again, and C's status will be changed from U to I, and then I will visit the only unvisited descendant of C, which is G, and change its status from U to I, and then I will find that there is no descendant node for G, so G will be automatically given a status C, and its sequence number will be 2. And finally I will go to the parent of G, which is C, where I will find that all the descendant nodes of C has already been visited. So C will also get a status C, and the level, I mean the sequence number will be 1. Okay. Now what is the output topological order? C, then G, then B, then A, then D, then E, then F, then H. This is the output. And it satisfies all the dependency constant. Is it acceptable?
Sir,
Yes.
sir, is the graph required to be connected?
Connected means, see, in case of directed graph, the undirected graph, connected and disconnected is very clearly defined. But in the directed graph, you can easily see this fully connected. It is not connected graph. This connected is called strongly connected. I mean, here you can easily see that there are different. That's why, I mean, it is, you cannot reach from any node to any other node. Not all nodes are reachable from all nodes. That's why we have to, the resultant DFS will will output 2 or more different DFS trees. Okay.
Yes, sir.
This is not disconnected, but it is not connected. So directed graph, there is a term called strongly connected graph. Okay, strongly connected component. So it will be, it is not like that definition of connectedness which we apply for undirected graph is applied here. But that doesn't matter for DFS. If it is not connected, that means there will be independent nodes. Okay, so you can separately order them. There will be no problem. If there is no edge from any portion of the graph to any other portion, that means those two sub-components can be solved separately in any order. No problem. Because these edges are very important. We need to respect this dependency relationship. Fine. If you have more than one component, no problem. You can take them separately in any order. Understood my point?
Yes, sir.
Now, finally, so application of topological sort already we have seen. Scheduling, it's very, very important application. Scheduling of task to satisfy data dependency constant, both in case of your single CPU environment and multiple CPU environment, like parallel processing. You can easily, I mean, you had digital logic class in third semester, na?
Yes, sir.
So there you have got an idea of digital circuit simulation. like finding the output of a circuit given the input?
Yes, sir.
Okay. So, how do you solve that problem? Suppose you have a circuit. Now, you apply the input that is available to all primary inputs. Now, how do you do? How do you get the final output? Just by simulation. How this simulation is done? So, you compute the output of all gates which are directly connected from the primary input, isn't it? Suppose there are primary input A, B, C, D, and you have a AND gate whose inputs are coming from A and C. Okay, now you easily can compute the output of that AND gate, and there is an OR gate which connects from 2 and 4. Then there may be another gate, XOR gate, which connects the output of that AND gate and OR gate. So that output of XOR gate can only be evaluated after you have evaluated the output of AND gate and OR gate in the second level. So suppose this is a circuit. Okay. So once you know the values for I1, I2, I3, you can compute the values for these two OR gates, G1 and G2. You cannot compute the output of O1, this AND gate, first. Before you have to compute the output for G1 and G2. Then only you can compute the output of this AND gate O1. Isn't it? So trivially, this circuit is already levelized in such a manner that you can easily see that the primary inputs are at level 0. Then all the gates whose input depends on the primary inputs appears in the level 1, and then the gate whose input depends on the output of this level 2 gates are appeared at level 3. Fine. Now, actually, when you find that, if you want to write a program which can take any digital circuit as circuit description as input and an input vector means the input combination of zeros and one for these primary inputs, and you have to compute the final output if you want to write a program, because this type of simulators are available. I don't know whether you have used that simulator tools for simulating any digital circuit. Have you used that? Any simulator tool to simulate a digital circuit?
No, sir, not yet.
Okay, fine. Since the lab sessions have not been there, so you have not yet. But anyway, you think of writing a program where you will be given a description of a circuit and an input vector. Now you have to compute the output. The circuit may be very large and the circuit description may not be like this figure. You cannot take a figure as input. There must be some data structure which can represent this circuit. You have to represent that. And the input description may be a file containing description like this. See, the same circuit, this file actually represents the same circuit of this example, like G0, G1, G2, G3 are primary input, G9 is the output, and like these are the descriptions. These are the intermediate gates. G4 is an AND gate which take inputs G0 and G1. G5 is another AND gate which takes input G1 and G2. G6, which is another AND gate, G2 and G3. G7 OR gate, G4 and G5. G8 is another OR gate, G5, G6. G9 is an AND gate. So this is not a picture, but you can easily visualize the circuit. So circuit basically comprises of 3 AND gate at level 1, followed by 2 OR gate at level 2, and finally one AND gate at level 3, isn't it? And see, these statements are ordered in such a way that if you follow this sequence, you will be able to find the output of various gates in one pass only, because see, G4 you can easily compute because G0 G1 will be available from input. Similarly, G5 can also be computed since G1 and G2 are primary input, it is available. Third statement can also be evaluated in the second time step. Then once these three statements are evaluated in any order in second step, you can easily evaluate it next two statements because their inputs are already available, G4, G5, G5, G6. Okay. And then in final step, you can evaluate this step. Understood? So this is a description which is already given in a levelized format. Just like in our, when we write program, actually we write all the computational steps when you write a C program or C++ program in a proper sequence. Compiler doesn't need to check or reorder the sequence. You follow the sequence of operation which has to be followed. Okay. But internally, if you give, just like in a statement, if you make a haphazard presentation of statement, similarly, the circuit description also, you can keep these statements in any order. Then the simulated tool need to identify in which order they should be evaluated, and that is called the levelization of the circuit. Okay. So circuit level, either without levelizing the circuit in proper manner, if you try to simulate, you will find that your simulation will be inefficient. It will take much longer time. In a single pass, it won't be able to simulate it. Like here it is levelized, that's why it is very trivial. So first step, all the input values are available. So now all the three statements in the second step which are at the level 1 can be computed in any order. Here I have chosen in this sequence. Fine. This order is not important, but they are, all of them can only be evaluated. I'll call you. Only be evaluated after this level 0 is done. Similarly, once all of these three group of statements have been evaluated, next two which are in the level 2 can be evaluated in any order, and finally the last statement which appears in the level 3. So this true value simulation can be performed in a single pass. Just in this array, you go in a pass, you will be able to evaluate them. But consider the same circuit description, I have changed the ordering of this statement in a bit. I have not followed the proper levelization. Then if we follow the same strategy, what will happen? G0, G1, G2, G3 will be available. Fine. But G4 will be, will be able to compute G4 because they depends on only primary inputs. But G7, see, this involves G4 and G5. But G5 is not evaluated yet. That statement appears somewhere here. So I won't be able to evaluate this statement if we follow this same sequence which is given. Then G6 is dependent on G2 and G3. Fine, I will be able to evaluate G6. Then G9, again I will not be able to evaluate G9. Then G5, I will be able to evaluate G5. G8, I won't be able to. So one pass is over. Since this description is not levelized in proper manner, what happened? I have three gates whose output I cannot evaluate in a single pass. I have to again perform a next pass. Then I will be able to evaluate G7 and this G8, but G9 will not be evaluated yet. Finally, I have to perform a third pass and this entire simulation process will be completed. So see, in the worst case, if my description is not levelized, I have to perform several passes. In the worst case, it may be equal to the number of levels in the circuit. And for a big circuit, number of levels may be very large. And so ultimately, my simulation program will be very inefficient. So all simulator programs, first, there is a pre-processing step. The input circuit description is first levelized, and accordingly this sequence of gates are ordered, and then this simulation is performed to make the simulation efficient. And you can easily see that whatever data structure you use to store the circuit, a proper ordering of gates is desirable. And often you will see this a digital circuit, basically a digital combinational circuit, not involving any memory element, only logic gates. They can be easily represented as a DAG. Okay, easily represented DAG, and these arrows are basically representing the input output relationship between the gates and the inputs, primary inputs. And the levelization actually means finding a topological order. Okay, so if your circuit look like this instead of this, the same thing, same circuit, this is sorry, a graphical representation, and same DAG can be redrawn in this manner following a topological sort. Now once you have redrawn this DAG in this manner, the levels are very much apparent. This is level 0, this is level 1, this is level 2, this is level 3. Okay, and the simulation will be straightforward and can be completed in a single pass. And you can easily see, you can follow the same strategy of solving this topological sort problem on this directed acyclic graph. Okay, so I am not showing this in detail. The idea is just to motivate you that how this topological sort on a DAG can be useful in solving problems which is a completely different domain of computer science. I mean, digital logic simulation, you cannot find, I mean, it is not quite apparent that there we can apply topological sort. So this is the beauty of this particular problem and this solution. Okay. So here also topological sort of a DAG may not be unique. So it is quite evident because the the gates, ordering of the gates in a within a particular level is not important. I mean, you can evaluate G4, then G6, then G5, no problem. But you cannot evaluate G7 before G4 or G5 or before G6. That is important. So this is also a beauty of topological sort, that this sort output is not unique. Within a sorted order, there will be some sub-order within which the ordering may be arbitrary, but those groups may be ordered properly in order to resolve or in order to meet the constraints, dependency constraint. In case of that statement scheduling, the data dependency, here also you can say this is the data dependency, but it is input output dependency. Okay. Okay, any doubts or any query?
No, sir.
So the participation is getting lesser and lesser. I think it's started with more than 30 in the first class, then it reduced to 25, 26. Now I have found in this class it is around 15. So it seems that you are not, many of you are not getting any interest. Anyway, so see, as I have mentioned it earlier, as I have discussed with Abhishek also, see, I'll be there if only one student wants to attend these classes seriously. Okay, uh, that's not problem. But as I have told him, I don't know whether he has shared or you understand this thing or not. It takes lot of effort from us. Okay, in order to prepare these slides. I don't know whether you appreciate or not. Uh, the preparation of these slides, preparation of this lecture takes huge involvement from us. Okay, so if we don't get that much response from you, it is really very difficult for us to motivate ourselves. Although I am saying that I will be there for a single student, but see, if I don't get enough motivation, my presentation will be poorer. Maybe, I mean, I will try to motivate myself from nothing, but still, as you can understand, this type of response will actually demoralize our effort, and maybe uh, the quality of the presentation will be not at par. So hopefully you'll be able to understand. I'm not forcing anyone to join. At least those who are present today, if you are interested, and if be frank, if you don't find interest, if you don't find it useful, you frankly share it with me. It is not a binding. I don't want to make it a binding to you. Okay, so if none of you feel interest, then also we can stop. Or if some of you still find some interest, you give that feedback to me. Okay, and also you just express some of your interaction with me in this class. Otherwise, it is becoming very boring for me, and it is like it has become a liability to me. So, as you know, in a professional world, this kind of thing is very demoralizing for us. Actually, we are also coping up. We have to put a lot of effort in preparing this type of slide. And right now, I am having um, several other courses going on. I have a first year course. I have which has already been started for last 1 month. Now, from this week, uh, 8th semester elective course will be starting. So I have lot of pressure, but still I love teaching. I love to share this thing with you. That's why I'll be trying my best. But you should at least show some positive response. Otherwise, it will be very difficult for us to continue with the same spirit which I have shown. Okay, so that is my point of view. So now when will be the next class? Shankita, uh,
Yes, sir.
so you just discuss with me uh, today evening so that we can
Okay,
fix
sir.
up next class if you want. Okay, you discuss with your friends also. If nobody wants, then we can stop here. If at least one or two people wants, I'll be there. You just let me know. Okay.
Okay, sir. I'll discuss with
So
them
that
and
we
let
can
you know.
fix up our next class, because as I have said, I have planned according to my plan. After this topological sort, I would like to discuss minimum spanning tree problem and their solution, and maybe single pair shortest path problem on graph.
Okay, sir.
Okay, that will complete graph. Then I want to discuss the integer sort, that means radix and counting sort, and hashing. Okay,
Okay, sir.
so I'll be needing few more classes. So if you are interested, you can just discuss with me, and based on our mutual uh, availability, we'll be arranging those classes. Okay.
Okay, sir.
So anything else someone wants to say? Should I conclude? Vishwajit, are you there?
Yes, sir.
So how you are finding these classes?
Sir, actually today I joined a bit late, so I missed some of the beginning part.
But wherever you have joined, or the other class lectures which I have
Yes, sir,
given
they were
earlier,
useful.
huh?
They were very fun. Yes, sir, they were very useful.
Okay. Popuri Charan, are you there?
Yes, sir.
So how do you find?
Yes, sir. It is quite useful.
Okay. Uh, Today I don't see that guy. I mean, this Projato is not there, na, today. Okay. Anyway, so let me hang up and probably we'll meet next. Okay. Bye.